So, hey, Ram and Paresh did a great job of allowing me to shortcut my presentation a lot. Hey, I do have a technical problem here. It is not doing the slideshow from the beginning. Yeah, what'd you do? I can't move this. That's cool.
Just go to. You're already on slideshow over there, by the way.
Oh, yeah. Cool. Got it. Okay. All right. Yeah. I should have figured that one out. Okay, cool. All right. So, I got about 23 slides. The good news is I can skip a lot of them due to Ram Paresh's presentation. A couple of very interesting things. Ram, you missed a really key point here. Rivian outscored Tesla on customer loyalty recently. So we're starting to see a lot of this in the electric vehicle segment.
I'll bring them up after they sell a few more cars.
Yeah. And Paresh, your V2G discussion is good because it fits right into this this discussion that I'm having. So with that, okay, what button do I hit?
You can do right.
Just
enter or the arrows.
Right arrow.
Enter or the arrows. Okay, fantastic. Now let's make sure this does this. Oh, it just blinked at me. This is no fun. Okay, so as she fixes that problem and teaches me how to use a computer, yeah, see, it's not just me.
Okay. Maximize your subscription.
A little introduction. So I'm Brian Engle. I'm Director of Business Development for Amphenol's Advanced Sensor Team. Amphenol's about a $14 billion connector company. It has about a $1 billion sensor company hidden underneath the folds of its skirts. It is quite active in this particular area of electrification. We provide a lot of high voltage componentry. And hey, look, you went to the right slide.
Yeah.
Okay, what do I do?
You can just hit the
Arrow key now? It's going to work? All right, good. Okay, so, and a couple of things beyond the day job is I also am president-elect of NATBAT, the National Alliance of Advanced Transportation Batteries, based here in the U.S. About 350 companies are involved, everybody from Piedmont Lithium extracting material out of the ground all the way through to the other end of the spectrum in the recycling chains. And I'm also chair of the SAE Battery Standard Steering Committee. That's about 1,100 engineers on 30 separate committees developing a variety of different battery safety standards and battery protocols. Also responsible for the SAE First Responders Task Force, which is why I talk a lot to people like Bobby Ruiz and the Hiller team. So a little bit about Amphenol. You can see here we've got a lot of product in this particular space. We're going to talk a little bit about today on a high level where we are in electrification and what we need to do with charging, some of the challenges that we have and what we need to go forward with. So I'm not going to read this slide. Real quick, there's already 41 million EVs on the road today, dominated largely by China. They are about 10 years ahead of us in deployment and technology. We're desperately trying to catch up with the BIL and the IRA. We have some challenges in the U.S. But it's more than just a vehicle. It's more than just a battery. It's a whole ecosystem. So you've actually got to look at the advantage that Tesla has had as an early adopter, early integrator, early inventor, so to speak, in this particular field. They recognized right away that in order to sell their cars, they had to have an excellent charging experience. And what you found from that is they developed their supercharger network, their home network. They were really very, very early in making sure that the vehicle and the charging infrastructure talked well to each other. And the end result of that is they've got about a 98% uptime of all their charging systems. And all you have to do is go look at the articles of the Ford CEO driving an e-Lightning and having disastrous results trying to engage public chargers and spending 4 hours trying to get 40% SOC from a lowly CCS1 charger. But anyway, we're seeing, really the whole infrastructure is about moving electrons. You're creating electrons within the grid. You are moving them to various points, consuming them in various application spaces. And with the cost of batteries coming down about 14% per year, this is only going to increase in deployment. It's not just about the environment. It's actually about performance improvement and economic factors that are driving electrification of many areas that are nothing like passenger cars. We're seeing a lot of deployment in industrial applications, electrified aircraft, agriculture, and mining. Huge advantages in having battery-powered mining equipment. So anyway, basically a little bit about the volatility of growth. China is the lion in the room right now. CATL is the biggest battery manufacturer by far. LG Energy System is kind of a distant second, and you can see there BYD being third. Panasonic squeezed out way to the right there. But basically, this industry's historically been dominated by the Chinese and the Koreans. But we are standing up an infrastructure for making batteries here in the U.S., and that's going to grow here too. We have a goal with the DOE Liebridge initiative of having 30 to 40% value add all in region for region from a completely vertically integrated material supply structure, refining and cell manufacturing by 2030. And right now we're on track to hit that number. So basically what we expect to see moving forward, past cars are everybody's focus, and everybody gets nervous every time there's new news. They're up, they're down, incentives are gone, incentives are back. The IRS says there's an FEOC thing last year. We went from 41 vehicles. They gave you the $7,500 down to 13 or 12. All of that's a lot of noise. Where the batteries are really well positioned going forward, especially the LFPs, is in the infrastructure, in the grid. Okay, we're going to see substantial growth in grid energy storage. We're going to see substantial growth in heavy-duty trucking, because the carbon footprint of heavy-duty trucking is huge compared to the scale of the vehicles that are on the road. So there's a great opportunity here, and we expect to see that overall this shift is going to continue globally. We're going to continue to trail China, but we're working to catch up. This is just a little bit about the grid infrastructure and support. I think Ram did a good job of summarizing this, but I did want to emphasize one thing here. The global demand for energy is going to be about 40 petawatt hours by 2050. And if you look at the base load levels here for general electricity demand, you can see the incremental for EV and electrified transport type systems is an incremental 15 to 20% growth on top of that. But hey, we all have all these electronic devices. I look at my shaving kit this morning, had 3 different electrically powered lithium-ion battery devices in it. So a little bit about the grid infrastructure support. So charging has been a bit of a challenge in the early generation of this technology. Regionally, we've had a lot of splits because we've got a lot of different grid infrastructures and we've had a lot of different players in the field. We have let's just say a vast array of experiments going on. So we have the old CHAdeMO, we've got CCS1, CCS2, which nobody likes, by the way. Great for home charging, awful for public charging. We've got the new Tesla NACS, which we just released at SAE, the J3400 standard, which now that Stellantis, Mr. Tavares recently announced that he's finally getting on board. We're going to have a common infrastructure for charging vehicles. And the advantage in this is not only that you'll be able to go to just about any station anywhere that's supported by the BIL, but you're going to be able to actually physically plug it into your vehicle, and it's going to have much better performance than a lot of the CCS1, CCS2 systems that are out there today in terms of its ability to carry power to your vehicle quickly and fast charge. And then over here to the left, we have MCS. Megawatt level charging. Ted Bond from Argonne leading a lot of that. That's going to go into a lot of heavy duty application spaces. You're literally talking about pushing a megawatt of power on those application spaces. This is just a little bit of what Amphenol is doing on that front. So we're providing basically the electron transport from the battery all the way to the motor. So all the high voltage busing, all the charge cables, all the receptacles, and you can see here that even amongst these verticals, you have basically, CCS light and then CCS heavy. And so what you've got is various current carrying requirements for different applications driving a variety of different designs here. And that's going to create some challenges because with those different configurations, you still have to have the same communication protocol. You still have to be able to have that I'm okay, you're okay between the charger and the vehicle. Now, a little bit about the EV infrastructure here in the U.S. This is the deployment. I think right now the DOE is modeling by, I think it's 2032, about 2 million charge points in the United States that are needed. BIL is a good Kickstarter for that, but we're really looking at trying to get 500,000 from BIL, public charge stations. Already got mapping in many of the states, the long-term plans for those states evolving. And then, that kicked off in December. We saw some of the first deployments of that, Pennsylvania, Ohio, kind of kicking things off for us. But a couple of items on the BIL. First of all, it requires 53% of the bill of material of those chargers has to be U.S. made. In addition to that, the requirement to get the tax benefit, 97% uptime. You cannot have defective, damaged chargers that just aren't doing the job. And then basically the 2 million used, and then the primary suppliers basically are listed down here. Like I said, you can see this after the event in detail, but we've got some good players out here. ABB, Tesla. I saw ABB is going to be down in the Expo Hall here. ChargePoint, a number of players who have been in the CCS1, CCS2 world who are rapidly moving over to the NAC standard. So when I look at the different systems, here's a nice little comparison of two different designs. So you got Electrify America and you got Tesla. Not being judgy here. I'm just saying these two systems have to work with the cars in the same way. They have to talk the same language, and they have to basically be dealt with in the same fashion, not only from everything from permitting and installation all the way through to the communications with the cars and then maintenance cycles. So you have to make sure that some way when one of these things goes down, or they're not going to qualify for that tax credit. This is just a quick image of what one of these typical depots looks like. There's all kinds of fancy pictures out there of what people, it's kind of like Starbucks on steroids kind of look. But effectively, many of these systems, when we go to the public charging, it looks a lot different than what I live in Florida. We got Wawa deploying 6 or 8 chargers on nearly every gas station. Those are small deployments. When we start getting to the pilots and the Flying J, you're going to be seeing 40 to 50 of these charge pedestals. And what you're going to end up with is you're going to end up with a whole DC energy storage, DC distribution, transformer technology. You're going to have cooling of these systems, a lot of underground high voltage cables. There's a lot of site work that has to be done to deploy these systems. So there's a lot of tear up to the infrastructure, but the infrastructure is more than just these. And that's what we're going to talk a little bit about in terms of the uptime and the behavior of these systems. The advantage, by the way, of that DC energy storage is now every one of those players can play an arbitrage. Now they can push and pull to the earlier discussion that we had on this. The challenge is making sure that we're talking to each other, and if something's wrong, we know it, and we're not pushing energy to the grid if there's a failure in the system. So this is just real quick a little bit about the 3400 and 1772 standards. So these are some documents we kicked out last year as that very panicky, quick response from the automakers when they realized that they needed to commonize around a single standard. SAE stepped in as an arbitrator, and we basically have now a generic standard that everybody can use. This is a typical new setup of the Tesla Gen.4. It's going to have 2 systems in it. It's going to be able to do the NAC standard for Tesla, but it's also going to be able to recognize that a non-Tesla vehicle just pulled up. I got to do CCS2. So it's automatically going to give you the adapter for CCS2 as opposed to the Tesla connector. That's great insight and forethought into those designs. So instead of having 2 cables, you only have 1. Now, some of the current issues with public charging, go online. The pictures are horrendous. Let's see, we got people missing the bollards and taking the systems out. We've got vandalism, cutting the cables off. We've got damage to the latches. We got people running over these things, and you can see tearing the cables apart, crushing the handles, a variety of different issues. Here's a nice one. This is a flooding issue from a few years ago. So these things can happen in these charger systems. What you really need to do is recognize that all of these different fault modes can cause issues, not only in the service of the device, but now it's potentially a safety hazard. So you need to be able to disable when you detect a critical fault in the system. So the charger manufacturers, those people on that earlier slide, need to do due diligence on their cell levels. Make sure that all the hazards are identified, recognized, detected, and countermeasures can be deployed. So they're going to have to incorporate diagnostics and support a very high level of uptime, safety, and fast repair. All right, so the SAE support of this. Our SMS, or Sustainable Mobility Solutions team, went out last year and worked with Charger Help, pulled together all of the information on the existing systems to be able to understand what are the typical problems we have. Top 4, station connectivity. Just being able to talk to the internet has been a problem for a lot of these Gen 1 systems. So when you can't talk to the internet, you can't charge. Internal station faults or errors, 38%. So these are a variety of different issues, whether it's an isolation fault, cooling system fault, over temp, bad relay, whatever. The pie chart's pretty deep on that one. Charging connector or cable damage, about 4% of the time. And then obviously the credit card reader. We've all had problems with credit card readers, so I think we all understand that's contributory too. So that's led Idaho National Lab and SAE to kind of work up what's called the CISPR, or the Charging System Performance Reporting. So the idea is, if you want to qualify for that credit, you need to have some sort of protocol everybody can use to make sure that those charger systems are meeting that requirement. And so these metrics were built according to USBIL guidelines. It's agnostic to the charger manufacturer and vehicle OEM. There's a whole series of tests going on between Argonne National Lab and the OEMs and the charger manufacturers to make sure all these systems are interoperable, that they can talk to each other. Which one?
The specs.
Yeah. Yep. Now, within that, there is a minimum suite of error codes required. So you can see here all the required diagnostics. You really need to be able to monitor for voltage, current, cable isolation, connector temperature sensors if you get a bad connector. If you're starting to get basically a resistive short somewhere, you're going to generate heat. You need to be able to detect that. Cable and connectors. Some of the megawatt level chargers actually use dielectrically cooled cables. So in the heavy truck depots, you're going to have a much beefier cable and handle because it's actually going to liquid cool. And then ambient temperature, make sure your heat rejection system is going to work properly. Lock position, a lot of proximity type sensors. And then the adapters, if you're using an adapter like Magic Dock, knowing that you have the temperature at either end of that adapter so you don't get any faults in that or you have a potential for arc flash. So you want to make sure you're monitoring that. And then additional sensors that are part of this are water intrusion for flooding events in any of the high voltage electronics and control systems. Coolant temperature, many of these are liquid cooled systems at the transformer level. Dielectric for the dielectrically cooled cables. Relative humidity, looking for condensation in the application, making sure that the cabinets don't get wet. And then high voltage IR based temperature sensing. I'll get into that in just a minute. And then basically a weather station, what things look like locally. This just looks across all the different sensors that you need in these applications. So if you're an AHJ, if you're a design house, if you're starting to look at installs for these, the key here is make sure that the charger, not just the charger, but the whole infrastructure behind it is doing appropriate levels of monitoring for diagnostics and has a full suite of diagnostics detection capability. This just kind of looks at the other half of that. So that was just the charger post and the inverter. Now we look across the rest of this and we see all of the other sensors that are required for the batteries, including thermal runaway monitoring, to Bobby's point earlier. An appropriate sensor could have detected that event and reported it the instant that first cell failed. Now, just a little bit about some of Amphenol's product along the way here. You know, we've got a full suite of these sensors. Basically, every one of the ones in red in the earlier slides are all sensors we provide today. This is a little bit of an interesting insight. So one of the challenges in monitoring high voltage components, there's a lot of heat rejection, especially in inverters. How do you monitor them safely? Because if you slap a thermistor or thermocouple on them, you have to put a high dielectric there, so you get really slow response. And then you got to worry about, well, does my sensor now become my fault path? In other words, I burn through my dielectric, I get damage, and now I got a shorting inverter at high voltage, which is never good. What our friends at that Tesla company did, they actually redeployed an Amphenol design from a medical application to start basically using an IEC 60664 capable system where they have an IR-based temperature monitoring of their FETs. So the big announcement February last year that they made about how they were cutting 30% of the FETs, that was why. because now they monitor the surface temperature of every component in the inverter, and they can very precisely manage that heat flux, which gives them the optimal performance of those inverter components, those FETs. So that's a kind of an interesting approach, but now we're seeing it deployed to monitor things like the cable junctions. So where you bolt the cables onto the buswork, where that might get a little bit loose and get hot, I can monitor that in a non-contact fashion with a high degree of accuracy and a fast response. This is just some of the other product that we're deploying in the field here. We use a lot of EMC resistant technology. We actually package a capacitor with our thermistor technology. So a lot of these high EM environments in the inverter, we can basically deal with that without having a shielded cable and all the stuff that an electrician has to do to install shielded, grounded cables like they do for the coax. The other thing we have here is leak detection, water intrusion. So basically, in one of these systems, we can detect with as little as a few millimeters of water or moisture or condensate in the high voltage electronics or control electronics. And then there's just packages for a lot of our other sensors that are deployed in field today on these applications. A little bit about our capability in current sensing as well here. There's a variety of current sensor suppliers. One of the kind of neat things that we have that we just launched is a new technology, tunnel magnetoresistive effect, or TMR, which has faster response, incredibly high accuracy. One of the advantages of this is you're charging for the amount of power flow you're getting through the system. You want to accurately measure that with something that's as certifiable as a state weights and measures decal that you get on the gas pump.